If you are a 3D artist, you certainly came across these three terms: textures, materials, and shaders. The question now is why we have all three terms and what is the difference between them. Also, want to use each one of them. Some 3D artists say materials and shaders are the same thing. You might also hear that materials are a combination of textures. So today, I'll try to shed some light on the topic and hopefully make it less ambiguous. We're gonna start with the simplest among the three, and that is textures. Simply put, a texture is an image or a pattern applied to a 3D model to give it color, detail, or surface texture for a lack of better term. Textures are like the skin or wrap that goes over the model's surface, and they are used to add realistic details such as wood and grain, stone surfaces, or skin tones without increasing the model's geometric complexity. And the thing is, a texture is usually just an image that is often simple and does not really show or help your model simulate how light should behave in real life. You can use, for example, a wooden texture and apply it to a floor to make it look like a wooden floor, or you can use that to visualize your interior design project, but the problem is this is not enough because it is too simple. That's why we need the other two. So on the other hand, a material is a broader concept that defines the overall appearance of a surface of a model, including its color, glossiness, reflectivity, normals, transparency, and more. And the interesting thing is that materials tell the render engine what the object should look like when light hits it. That's why you can't render good-looking surfaces using only a texture. But let me elaborate more. Materials combine a set of textures, or commonly called maps, and set parameters for how these maps should interact with light and the viewing environment. But they can be simple, like a single color, or complex, using multiple texture layers and light interaction properties. But what about shaders, you might ask? Well, shaders are surprisingly simple and complex at the same time, and I will explain that in a minute. At a very basic level, or I should say at the very core, shaders are small programs written in a specific shading language, like GSL or HLSL. And these languages tell the computer how to render each pixel of the material. Shaders calculate effects such as light, shadow, reflection, and texture mapping on the fly. And this is where things start to be confusing. But to simplify it, shaders control how materials are visually represented on the screen, manipulating factors like lighting calculations, surface shading, and post-processing effects. And they are crucial for creating dynamic visual effects and realistic interactions between light and materials. But you might say, hold on, shaders create materials, what are you even talking about? And here's the thing, a shader can be any surface you can see on the 3D viewport, with or without a texture or a material. Because to be able to see the default cube, for example, in Blender, you will need shading. Also, some people use the term material and shader interchangeably, which is confusing to some. Before we continue, let me tell you about this. It is amazing how many things Blender can do, from scripting, compositing, camera tracking, video editing, you name it. But one thing that I think is the most overlooked and underutilized in Blender is the Grease Pencil. Grease Pencil is a powerful tool that allows you to bring your 2D sketches to life in a 3D environment. So today I present to you, hands down, one of the best Grease Pencil courses on the market right now. If you wanted to learn about Grease Pencil before but couldn't find an easy way to do so, this course called Draw from CG Cookie is the best way to start. The best thing about this course is that you don't need any prior knowledge that you will start with, so you're gonna learn the absolute fundamentals from the toolbox, colors and materials, brushes, modifiers, effects, and finishing with the animation and putting what you learned into actual projects. So what are you waiting for? Click the link in the description and start your awesome Grease Pencil journey right now. And since I mentioned the default cube, let me give Blender as an example. Blender uses a shading language called Open Shading Language, or OSL, to define surface appearances. But right now, I think I'm getting a little bit ahead of myself, so real quick, in less than 2 minutes, let me give you a quick history lesson so you can understand shading better. Back in the day, before we were able to use advanced shading languages to be able to visualize surfaces, things were much simpler and straightforward. But not really, if we are talking about difficulty and complexity, because honestly, I think shading was never simple to begin with, especially when we talk about the math involved and stuff. Anyways, in the early days, I believe the only way of shading surfaces was flat shading. This method computes lighting for a single point per polygon, usually a vertex, and then applies this uniform lighting across the entire polygon. In English, it means each polygon is responsible for only one color, let's say. After that, in 1971, Henry Gouraud came with the Gouraud shading, which is an improvement over flat shading. It calculates lighting at each vertex of a polygon and then interpolates these lighting values across the surface. This results in a smoother appearance, where color transitions between vertices appear more gradual and less faceted than flat shading, which I think where things started to get more interesting. But why not make it more interesting with Feng shading, which was introduced in 1973 by Tuong Feng, which basically improved upon Gouraud shading by interpolating normals instead of colors across the surface and computing lighting at each pixel, which is far better, I would say. This allows for more accurate rendering of specular lighting and gives a smoother appearance to the surface of any 3D model. And as you can see, this was back in the 70s. But now we have what we call programmable shading languages, which are based on the shading theories and principles I just mentioned. Languages such as HLSL, GLSL, OSL, and CG. Now, going back to the example of Blender, OSL is a high-level, programmable shading language designed specifically for rendering, allowing you to write custom shaders for various effects. It is actually integrated into Blender's Cycles rendering engine, enabling the creation of complex materials with customizable behavior. And when it comes to real-time rendering, Blender also supports the use of GLSL, which is OpenGL shading language, within the Eevee render engine. GLSL is a common shading language that interacts closely with the GPU, enabling real-time previews of shaders and materials during the modeling process, or when you are working on your project generally speaking. When it comes to other 3D software, Max primarily uses HLSL, which is Microsoft shading language for use with the DirectX API. Additionally, Max also supports CG, or C for graphics, developed by NVIDIA. On the other hand, Maya utilizes HLSL, GLSL, and CG, and it integrates closely with Arnold, which uses a node-based approach to shading that can be extended with OSL. Cinema 4D supports GLSL for its real-time preview and rendering capabilities, and it also uses its own shading language within the node-based material system. But the next two are different and interesting to say the least. We have Houdini, that is known for its flexibility and supports VEX, vector expressions, a high-performance expression language, somewhat similar to C, that is specifically designed for writing shaders. On the other hand, ZBrush is primarily a sculpting tool and does not use the conventional shading languages like other 3D software, because it has a unique material and rendering system that is more integrated and does not allow for traditional shading programming. However, it can export maps and geometry for use in other programs which support shader languages. Otherwise, it's gonna be hard to go back and forth between different 3D software. I know this is not enough to understand what shaders are, but I hope this gave you a general idea. And now, let's see how each one of them is made, which I think will also help. And let's start with textures. First of all, a widely used tool or method for creating custom textures is using software such as Photoshop or similar 2D software. And this was the case especially in the early days, like the early 2000s or even early 2010s. Artists can use layers, filters, and brushes in Photoshop to craft detailed textures from scratch or modify existing images. Another method is using photographs or real materials, Usually you can create highly realistic textures using this method, and this involves taking pictures of relevant surfaces and then applying these images as textures onto your 3D model, adjusting for scale and distortion to ensure accuracy and realism, which I would say is really hard to achieve only using textures. And for a more artistic or stylized textures, some developers or designers prefer to hand draw their textures, scan them, and then apply them onto their 3D models using UV maps. This method is particularly popular in game design and animation where unique and stylized visuals are often required. On the other hand, making materials can be done using different methods. For example, you can build your material by connecting nodes, and these nodes can generate patterns like noises or shapes, transform inputs, and simulate physical properties like roughness, metallic surfaces, and basically you can do this in a lot of 3D software because a lot of them have node material editors. Each node performs a specific function, and combining them allows you to create complex results. The other method which I personally prefer, which is using software such as Substance Painter and Substance Designer, which is geared towards creating physically based rendering materials, or PBR materials. This means your materials will realistically react to light and shadow based on their physical properties, and this is achieved through maps like albedo, normals, roughness, and metallic, just to name a few. Last but not least, let's see in a nutshell how shaders are made. For those comfortable with coding, writing shaders from scratch using a shader language like GLSL or HLSL can be a really powerful method, but I don't think the majority of 3D artists are good when it comes to that. However, this approach allows for maximum flexibility and control over the graphics when rendered on a GPU. You can start by understanding the basics of shader codes, such as creating simple color shaders, and then move towards more complex effects like lighting and texturing. Another method, and this one is more popular, which is using nodes to create complex shaders. You can combine different shader nodes using a mixed shader node to blend different materials or effects. For example, mixing a glossy BSDF with a diffuse BSDF can create a surface that simulates both rough and shiny properties. And there you have it, guys. I hope you found this video useful and informative. If you did, please give it a thumbs up. You can also subscribe to this channel to receive more videos like this. Thank you guys very much for watching, and I will see you in the next one.